Alrighty, let's go ahead and have some fun here. Hey babies. So, let's do some lambda calculus work here. I created a new syntax about 6 or 7 years ago. So I'm babies. So I'm just going to share it with you guys because I didn't share it really online. I wasn't posting my code. I was making a lambda calculus reducer. So you know, it gets confusing because you can never really tell what's really going on. Like, let's say you have lambda x dot x, and then you have x applied to x, and then say you want to apply that to another, you know, another lambda expression. And so now you have to sort of figure out that this thing is applying to that, and you have to know, without wanting to mess around with parentheses too much, what's going on. No. Here's the interesting thing, right? So here's a syntax that I came up with so that you can use it in computers and you never have to worry about being confused about what's going on. Now, there's this interesting sequence of numbers called the Catalan sequence, the Catalan numbers. They're very interesting because they have this property where you're never confused about where something is when it comes to being a left child or a right child. Okay, so I can put parentheses inside of here. I can put parentheses on the right side, and that's the same as having a structure like that. Notice how I'm not using the left side or the right side. I'm only using the right side because otherwise you don't get that availability to parse the ambiguity. So you can use this to your advantage to represent the applications, because remember, there's variables in traditional syntax, there's variables, abstractions, and applications. And applications get confusing because remember, lambda calculus has these different ways you can use it, right? You can reduce it in different orders. You can reduce the function first, you can apply the function first, or you can reduce the argument first, and you'll still get eventually the same result. And yet it still matters which one you're applying as far as order of operation, because you can have f of g, but you can also get confused on whether it's f of g or f applied to something and then that applied to g. And that's different because it's not just the order that you're reducing something in, it's actually the order of the containment of the functions. And that gets confusing when you have this currying going on. So I got rid of sort of the ambiguity with the currying. So for applications, I actually use brackets, okay? There's two options for abstractions. You can use a dot, or you can use parentheses. So the first version I made used parentheses. The second version uses dots, okay? I made the syntax. It's not on Wikipedia yet, but I made the syntax about 6-7 years ago. We also have numbers for De Bruijn. So 1, 2, 3, okay? So what that represents are basically the same thing as variables. So we're going to go ahead and do an example here. So this is very, very straightforward how this works, all right? So if you have, let's say, lambda x dot x, okay? Just the identity function, very simple, okay? You have one abstraction, and then you have a variable, and the variable is pointing to the closest thing outside of it. Okay, so the way we write that in our first syntax is just like that. The parentheses is the same as the lambda, and the 1 represents the x, and it's saying go refer to those parentheses out there, okay? Another way for syntax number 2, version 2 I should call it, you know, it would just be dot 1, okay? So all three of these mean the same thing. They're just different syntax, but I'm going to show you why mine gets less confusing when you get really complicated, because when you start working in code, you have really long expression that represents, say, applying the Ackermann function of 3 and 2, and it takes up like 20 lines of code, and it's a bunch of brackets and things like that. Now, it would be really confusing to parse. It's really confusing to select the function part of it and to deal with it if you don't have a syntax that you can't unambiguously use. So that's where it really comes into play, these brackets. So if I say something like 1, 1, okay? So this would be an example in syntax number 1 of applying this abstraction to this one. So that would be just applying lambda x dot x, which is this, to lambda x dot x over here. Okay, so usually in lambda calculus, the traditional model, you'd have to think about whether you need parentheses or not to basically get rid of ambiguity. And it's kind of confusing when you need it or when you don't, because you have to know where the context is. In here, it's always explicit. You always know exactly the ambiguity. Syntax number 2, again, you still need brackets. Why? Because with applications, you're taking advantage of the Catalan structure. When it comes to the parentheses, though, you don't really need it because they're always contained, so they always mean the same thing. So you're not using the fact that you put something inside and to the right of. You're only putting things inside. Okay, you're only nesting inside, and because of that, you can change it to a dot, and you don't need to mark the end of it because there's no ambiguity of what's the end. You can put dots in front of some expression, and you'll never be confused about really too much what the end of it is. Now, with the brackets, you do need to mark, to be able to nest them, it gets really complicated because you're going to have nested brackets, okay? So traditional lambda calculus, maybe you'll need the parentheses to be able to tell what's the difference, because is this x applied to that, or is it this whole expression applied to this whole expression? Those are two different things. Whereas here, it's explicit. You know that whatever's inside is being applied to whatever is on the right, right? So there's no confusion about what is being applied to what here. So when you start looking at really big expressions, by the way, I never do those by hand. They always get complicated. If you're just adding two numbers, it's already more complicated than doing an exponent, okay? I don't even do that by hand. I don't do 1 plus 1 by hand because in lambda calculus, 1 plus 1, the simplest known forms of that is still really, really complicated. It still takes who knows, 30 to 50 steps. It's really obnoxious. So the whole point of the lambda calculus being Turing complete is to allow expressiveness, but it's not that you're doing the computations directly in lambda calculus as the optimal form, as the most efficient form of computation that we really know would expect. But it is a useful language to express types, languages in general, the structures of languages, because it's an optimally sort of simplistic form. Okay, it gets rid of all the complexity and leaves us with one simple grammar that's Turing complete, that's computational. So you can nest these, right? So if I have, say I have an expression in here, A, and A is going to be applied to another expression, B, and then that expression is applied to C, okay? That's different, okay, than if we took A and we applied it to B, which is applied to C, okay? So what are these two things, right? These are two different structures here. So we have our root, okay, which is going to be on this top one, it's going to be something on the left applied to C, and the thing on the left is going to be A applied to B, okay? So you're going to have A and you're going to have B. You're going to apply that to C, okay? That's different from this, which is A applied to something, right? So you're going to have A on the left, and that's going to be B applied to C, okay? So there's no confusion about whether you include, whenever you have an application, you include the brackets, okay? Notice there's no parentheses, and that's just because whatever A and B happen to be, I'm representing them just as meta variables right here. So that's not part of the core syntax, but if you want to abstract on the syntax, replace something like, say A is just defined as maybe something like that, okay? Now here's another thing, is because I'm using de Bruijn indices, there's a context situation here that's different from using the variables, because when you're using variables, the expressions, the context will matter as to what the variables are referring to. Whereas when you use numbers, yeah, the context matters if the numbers go outside of it. But the expression itself is sort of the same thing, and you don't have to worry about rewriting variables at that point. So, like in traditional lambda calculus, you might have something, and then you have another nested x, right? And you might want to change this to a lambda y dot y, okay, to say that it's the same thing using a different type of conversion, right? But the problem is, what if I change this one to a y first, and I'm only looking at this expression? Now we have all these different variables. Whereas if you're looking at de Bruijn indices, which I didn't invent de Bruijn indices, right? I'm just using them. They already exist. So if you use de Bruijn indices, like if I do a 2, let's say I do 1 and 2 here, okay? So what this is referring to is this 1 is referring to here, and the 2 is referring to there. So it's kind of like having a lambda y dot lambda x, right? And then it's this inner one, x applied to y. Okay, now that could get confusing if you start appending things to it, but in my syntax right here, first of all, you can tell that the 1 and the 2, just by going out enough parentheses, you know that that's a complete context-contained expression, okay? And you don't have to worry about how, if you're going to apply this whole thing to something else, you're going to have to do something like that, right? Whereas here, you put an A, maybe you put parentheses here, maybe not, and it gets confusing, okay? So in syntax number 1, that's how you'd write it, okay? In syntax number 2, okay, you see that? See how simple that is? Okay? And if we want to expand it to that other expression, we just add parentheses around, brackets, I should say, around that. And there you go. Okay? So, syntax number 1, syntax number 2, pretty straightforward. When you start using code, you can see that there's certain expressions that are just different from others depending on how you've nested these brackets. And that explicitly lets you see what function is being applied to what. Is it f applied to g and then that's applied to x, or is it f applied to g applied to x? And it's already confusing enough, right, to have to figure that out when you already are dealing with the fact that lambda calculus lets you sort of research it, lets you reduce things in different orders. You can always reduce f first and then apply it to g. You can apply f to g first, or you can reduce g first And then you can take all three of those and try to do research and compare what's going on between all those different possibilities. And that's going to be really confusing if you already can't tell what's actually the correct expression or not, right? You need code that can check what is equal to what the value of something is, how to interpret it, and is there only one way to write it? In my syntax, there's really only one way to write it too, so that's another type of ambiguity, but it's helpful to have that, to not have to decide whether we're going to add parentheses or not. Okay, in my syntax, the decision whether you have brackets or parentheses are explicitly only one option everywhere. So either there's a dot there or there's not, and it's a different expression if there isn't. Either there's brackets there or there's not, and either it's a valid expression or it's not, but if you remove or you add the brackets, it's going to be a different expression. It's going to have a different meaning. It's going to be a completely different lambda expression. Whereas in the traditional math, sometimes you can add parentheses or you can remove them, and you can't really tell whether adding them or removing them gives you a different expression or not. And that's another ambiguity. It's not just the ambiguity of having two syntax trees that are possible for the same expression, but it's also the ambiguity of can you have two expressions representing the same actual syntax tree. So there you guys go. Lambda calculus syntax version 1 and 2 that I created. And also, I think I'm going to start doing my videos in a way where instead of getting frustrated with my dog making some noise in the background, I'll just let her join in on the video, because she's a really sensitive dog. And sometimes I'll try to quiet her down, make my little video, and then continue on with life. But instead, I should just include her and let her be more herself, because she's actually a very sensitive and sweet dog. So I'll see you guys in another video. Thanks for watching.